Okay. Thanks for coming to my session. My name is Hajime Tazaki from IAGRAO. This work is joint work with my friends Ryo Nakamura from University of Tokyo. It is about the kernel offloading stuff in general. So this talk is focusing on the kernel offload, but mostly focusing on the TCP offload engine, which we historically discussed a lot in the past. So TCP has various options to offload some of the computation from the host operating system to the external devices, like checksum offload is almost common, or segmentation offloading is also important to accelerate the performance of the bulk transmission. But the TCP offload engine, on the other hand, is trying to fully offload the TCP processing from the host operating system to the external devices. Historically, we are focusing on network interface card for the offloaded devices. And the motivation for this TOE or TCP offload engine is to save the CPU cycle from the host operating system and offload those heavy tasks to the NIC. And also trying to save the memory operation between the NIC, between the application to the kernel or application to the devices, and trying to contaminate within the processes within the offloaded devices. And as a bonus option, if the data is on the external devices, the memory copy between the application and the NIC is also reduced and offloaded. So the basic idea of TOE is do heavy lifting all the stuff in the hardware, not in the host operating system. But the TOE has been unrecommended in the past 20 years, I believe. The Linux kernel never accepted the TCP offload engine patch set, which originally proposed during around 2005. And Microsoft has also deprecated some of the TOE-related feature in the older version of the Windows operating system. So if I understand correctly, the first attempt to upstream the TOE framework was done by the Chelsea around 2005. So their proposal of the patch set is to propose an abstract framework for the various TOE implementation. So to put the various hooks on the TCP core part of the TCP implementation, and call the external function based on the vendor-specific interfaces. But the reaction of the community, especially in the Linux kernel community, was not positive because of if the security issue has been discovered in the TOE implementation, it is very hard to update or replace the implementation in a timely manner. And also, as the TCP implementation is very original, the Linux feature, especially for the packet filtering feature like a net filter, is not available for this particular TCP implementation. And the community after this discussion was summarizing the reason of the rejection of this patch set. So in this wiki page, I just randomly Googling this page to look at why TOE patch set was rejected. So there are 14 distinct reasons, but we can summarize it in the 4 different categories. So most of the notable rejection reason that I think was the lack of feature set in the TOE and TOE implementation. Like as I mentioned, that the TOE, hardware-based TOE doesn't have a net filter functionality. And also, compared to the maturity of the TCP implementation in the Linux kernel, and the vendor-specific TCP implementation has not been very well tested in terms of the interoperability. So it lacks a kind of RFC compliance in the TOE implementation. And also, it also requires the different tool set to configure the vendor-specific TOE. And also, as the different implementation has been exist in the single host, the global view of the TCP implementation has been observed in a different way. So it was about the 2005, mostly 20 years ago, and it's now it's already spent so much time. And now network interface card has a software-based ability to update the code inside the NIC, which is called smart NICs on DPUs. And they can run the Linux instance within the network interface card. So we believe now is the time to try the TOE again after the 20 years. So our approach is to offload all the kernel functionality from the host operating system to NICs, as I described in the bottom pictures. So typical kernel user space is host operating system has the left side figure like this. But we tried to move this green part from host operating system to the hardware side. And I tried to connect this decoupled, splitted part of the communication, splitted part of the implementation by our own communication channel between them. So we call our implementation as Mino or Mino. It's a random and a tentative name, so it's going to be changed in the future. But the basic idea of this Mino is to split the kernel and the kernel from the host operating system and move to the network interface card. And we designed, implemented our private channel to communicate the user service application to the kernel moved to the network interface card based on the RDMA channel which we used. And the benefit of this abstraction is we don't have to change any binary or application programming interface between the user space and the kernel programs, because we just moved. We didn't use a different implementation from the Linux TCP implementation to our offloaded engine. And it means the existing toolset like IP route 2 or the shell script passing the proc and the system, sysfile system can be used as is. And thanks to the clean abstraction, this offloaded part can be replaceable. So it's programmable. The kernel implementation can be used in a different way. And it is also, the TCP implementation part is still software-based, even though it is running on the hardware, it is running on the NIC. So it is still updatable if we will face some security threat in the future. So let me try to describe more detail about how it works in the internals. So the basic procedure for the system call processing in the typical Linux kernel hardware, a kernel host operating system, is just put the system call number in the register and trigger a special instruction to the kernel space. And the system call handler in the kernel side trying to copy the memory specified in the system call argument by copy from user function, and also notify the buffer to the user space by a copy to user function. So we utilize this functionality to implement the private channel between the NIC and the host. So we just use this notification for the system call with the system call and the argument, system call argument. But the copy from user interface implements the communication using the RDMA channel between the NIC and the host. So by using this interface, we don't have to change any other part of the kernel as well as the user space part. So using this one, this interface, how it works in the typical use cases. So host part, we have to use the minor or minor client -c for the launcher program of this offloading function. So this launcher program first tried to hook the system call of the user space program. Our current implementation is based on the LD preload, but the LD preload is not perfect, so we are trying to integrate with the more flexible framework, which is called Z-point, as I pointed in this, put the pointer in this slide. And this intermediate program, after hooking the system call, this intermediate program copy the system call number and the buffer from the user space application and they copy the information to the NIC via our private channel. And in order to avoid the number of the memory copy operation, we register the particular buffer from the user space application to the RDMA library. And the user space program waits the result from the response from the DPU side and receive the return code and the error number as a typical function call from the system call invocation. And for the NIC part, you have to use the daemon program in the NIC side. And this daemon program is currently implemented as a user space application, but it can be run on the kernel module if we have another implementation. And this daemon program waits for a system call request from the user space program by our own character devices. And once the request is accepted or received, the daemon program processes the system call and they copy the memory buffer from the copy from user function, as I mentioned before. And after that, it goes the regular path of the system call handling within the NIC side. And the post result to the query, the user space function, user space program by a copy to user function call. So our current implementation of the NIC side daemon is based on the Linux kernel library. It's out of 3 Linux kernel implementation, which aim to reuse in the different environment, not only for the monolithic kernel. So we adapted this library as a user space program, just attached the Linux kernel library, shared library into our daemon program. But this is just an option that we took, but you can also implement another way, like to implement a system call proxy in the Linux kernel module, and call the host kernel of this DPU side, NIC side, after receiving the system call in the proxy implementation. So looking at the different implementation, different project which has a similar goals as we have. So there are several academic studies available in this area. So the net kernel has been implementing a kind of split kernel between the virtual machine and the host operating system. And if the network stack in the virtual machine has been called, it will be forwarded to the host kernel. The host kernel part implemented the various pluggable TCP implementation. They has implemented with the MTCP, one of the user space TCP stack, or an extension of the Linux kernel. FlexTOE has almost similar. TAS is another user space TCP stack, and they are targeting on offloading this TCP functionality to the smart NIC. IOTCP is also similar, has similar architecture, but they are mostly focusing on the send file system called offloading from the host to the smart NIC. And also Chelsea still has the classical type of TOE at this moment. So we conducted kind of qualitative quantitative analysis on the different implementation based on the criteria that has been discussed in the kernel community with the 14 different criteria. So the original situation of what Chelsea has been proposed is not changed after the 20 years, I believe. They still have a good number of the performance, but the various concerns still exist in their implementation because of this, the hardware-based implementation of the TOE. While NetKernel FlexTOE IOTCP has been based on the software-based TCP offload engine, so they relaxes several concerns on the original TOE concerns. But the implementation of the TCP itself is very private one, not a Linux-based one. So lack of feature is still exists on this type of implementation. On the other hand, we have been used the Linux kernel as a offloaded engine of the TCP implementation. So we can fix all the concerns by using our implementation. But the number 14 is kind of the visibility of the resource available from the software implementation. And we have same concern at this moment for the sake of simplicity, because the NIC side and the host side still has a different instance of the Linux, but share the most of the information, most of the resource between them. But if you look at this node from the outside of host, it should be able to be, it should be a single host, but it should be visible as a multiple host. This can be improved in the future by changing the implementation. And what we didn't answer for the moment is how this perform well when we offload this, when we use this offload functionality. I'm going to show you later. So before going to demonstrate showing the result of benchmark, I'm going to show you a demo. So this is a typical, So this is a typical host of the Intel machine, which runs the slightly older version of the Linux kernel. So I'm going to split. So on the top pane, it is running. It is a console of the DPU side, which is based on the which is Bluefield 2 of the NVIDIA. Oops. So which runs a slightly older version of the kernel. And on this DPU side, we are gonna run minor daemon with this JSON configuration file for the kernel configuration for the initial invocation. It takes a while to finish the boot. So on the other hand, the host side is trying to invocate a typical user space program. So in this example, we use the Dash, one of the shell implementation of the Debian-based distribution, with the Mino client launcher for the offloading function. So this is running, this shell is connecting to the DPU side, and this DPU part implements the different kernel version with the 6.5 and 6.1. And the architecture is also totally different from what you have known, which is based on the LKL. So all the user space tools should be available as it, like IP route command or ping to the external node is also available as it. And also syscontrol command should be also available as is. You can also look at the proc file system in, proc file system based on the Linux kernel library implementation. You can also run the netpath command. Okay. As you could see with the typical host operating system. Okay. So I'm going to go back to the rest of the slide. Okay. So we conducted a kind of preliminary benchmark based on our prototype implementation using two different machines connected back by the Bluefield 2 with the 200 gig Ethernet port. The version we used for the Bluefield 2 has 8 ARM cores with a 15 and 16 gigabyte RAM. And the workload that we use is the netpath with the TCP stream scenario as well as the TCP send file scenario. And also we also try to utilize the KTLS functionality with the OpenSSL integration over the Nginx implementation. The first benchmark is using netpath, which has 2 different modes. So typical netpath, as I demonstrated before, was using a send message system call, which copied the memory buffer from the application to the NIC during the benchmark. While the send file system scenario, the buffer for the transmission information should be copied within the NIC site from the file system visible from the Linux kernel library inside the smart NIC. So the send file benchmark should benefit a lot compared to the typical send message version. So here is the result. So the purple bar and the green bar is the result of the host one without offloading, while blue and the orange one is the offloaded version. And the point plot showing the yellow, blue, red, black was the CPU utilization measured by the time command. So the good put result, the performance result of the host one is always outperformed to the minor implementation, unfortunately. And the CPU, if you look at the CPU usage, the minor one is almost recording mostly 0%, while the host version uses a reasonable amount of the CPU utilization. And for the send file benchmark, we didn't see much stable result from both in the host and the offloaded version. Like this green one is the send file message, and it should be better than the send message version, but in the several pattern of our benchmark scenario, it didn't show the benefit of the send file system call. And for the Nginx benchmark, we used the recent version of the Nginx with the non-default build option with enabling the KTLS functionality, and also enable the send file system call over the configuration file. And we stressed this Nginx instances by WRK tools for the web client. So here is another result of this Nginx benchmark. The color and the bar is almost same as the netpath version. And as you can see, offloaded version is not performing well compared to the non-offloaded version. So the good put is all as same as the netpath result. The performance of the good put result is in the host operating system is always outperforming to the offloaded version. And the CPU usage also shows the similar characteristics. With the offloaded version, the usage is slightly lower than the host non-flooded version, but it is also showing that there is no high load incurred to the offloaded version as the result of the good put measurement shows. It is almost under maybe 10 or 20 times slower than the non-offloaded version. So if you look at the frame graph of the offloaded implementation, and most of the process is using recording the encryption part in the TLS send file system call. Because we didn't use the crypto offloading function at this moment. So if we implemented it, maybe it can be improved on the TLS workload of this offloaded benchmark. So here is the result as on the qualitative analysis. Fortunately, at this moment, we don't have a good performance characteristics in the minor D implementation. So if we look at more closely of the result of that we obtained, the bottleneck might be because of the private memory channel between the host and NIC that we implemented. Because if we run the netpath session on this smart NIC without any host interaction, the result is way faster than the offloaded version. So there should be some bottleneck is this our implementation. And also, even though this private channel has been improved, we will face some limit on the hardware capability of the Bluefield 2 that we have been using right now, because the interface itself has a 200 gig NIC on the Bluefield 2, but we cannot utilize full of the availability bandwidth available with this our current implementation, our current devices. So it might be not so powerful compared to the typical Intel machines. But our design trying to satisfy all the ideal TOE implementation, which has been discussed 20 years ago, by reducing the CPU and the memory usage on the host and trying to implement the software-based TCP implementation, but mostly identical as the host operating system. But unfortunately, we don't have no performance gain when we use the offload engine. So I'm going to skip several parts. So to summarize my talk, so we have been presented about our kernel offload functionality, which is calling MINO, to decrease the CPU load from the host operating system. And the benefit is transparency of the application, as well as the kernel implementation of the Linux kernel. And our approach is trying to address the TOE concerns, which has been discussed 20 years ago. But so far, we don't have no performance gain at this moment. So that's almost it for me. Thank you for listening.
Questions? So before he gets to it, did you measure the latency? Because you're offloading the system calls, right?
Yep.
The 99th percentile, for example.
We didn't have a latency result, but
okay. But with WRK, you can probably get it.
Mm-hmm. Yeah, so I had two questions. One is, did you measure syscall rate? Because I think your bandwidth problem is a syscall rate problem or a latency problem. One way or the other, there is some tuning to be done there. But the more interesting question in my mind is, it sounds like what you're proposing is a generic syscall offload. You can actually just take the hypervisor out of the picture by just doing
indeed
a standard DMA out. So have you considered what that means? Because now you have kernel objects that you need to reference, but this is not just a pure networking solution at this point.
Yeah, it's a very good point. I mean, so actually we are trying to capture the system call procedure and trying to offload to the external devices, but it's not system call at all. I mean, how can I say? It's a very kind of tricks that the user space implementation can take, like a kernel bypass technology also take a similar approaches. But yeah, I agree. I agree with the point of what you mentioned.
I just wanted to point out that the history here goes way back even further. One of my first projects as a young engineer was to get TCP/IP running on a RAID-CAL Interland 286 card and 64K of RAM. It didn't work very well there either, but I appreciate you trying. My core question, though, was, have you considered looking at the shaping problem?
Yeah, we haven't been looked at very detailed scenario, but it's very nice to see in the future.
Yeah, hi. I was going to make a similar comment as Dave, because we were running Linux and Linux kernel on SmartNIC in 2004. I'm also glad that we didn't fail miserably back then. But looking back at the talks that were yesterday, that Google was talking about the DMA straight into user space and the I/O U-Rings. How would that match with your work? And feels to me like the I/O U-Rings could be mapped straight to your SmartNIC in some way.
So are you asking about the applicability of the, for example, the I/O U-Ring in this design, or?
Yeah, how would it match with these two designs, the two approaches that seem to land in Linux soon, and with your offloading to SmartNIC?
Yeah, if this kind of new functionality only involved within the kernel, maybe it can be adapted as is. I mean, our kernel offloaded implementation is very independent from the user space implementation, so it should be fine, I believe.
So did you look at, instead of trying to hide and make it transparent to the application, actually make the application aware that it was offloading this transmission or reception to the SmartNIC?
Yes.
And did that have any improvements? So it seems like some of your costs might be in the fact you're trying to hide it and make it transparent to an application that it's being offloaded, where if you do it up front, then the setup costs will be gone and you're just pushing requests like an RDMA style right down to the NIC. And so I would expect it to be a lot better.
Yeah, when we started this project, we are very optimistic. We didn't have such a serious concern on the various scenario, various use cases, but it was tried to see more in detail.
Yeah, I'll have one more question.
Okay.
Because this is essentially like adding a CPU to your system, right? Which is kind of like maybe a price NIC. How would it compare to, like, say, dedicating a couple cores or having a couple more CPUs on the host?
On the host, yes. That should be very definitely considerable option. I mean, yes, SmartNIC or XPU right now is not so reasonable solution option that we can consider, while the maybe increasing number of these cores in the host side should be very cheap. So it should be another option that we can consider, this adapting this design to the different scenario.
Another question about the transparent interface. Here.
Okay.
Hi. It can never be perfectly transparent, right? Because if an application wants to do something like send file, it's going to fail because your file descriptors are basically on two different cores. So applications will have to opt into this scheme. I guess that's one question.
Yes.
And second, if you have a large workload with many flows, these SmartNIC cores are relatively few and small. Have you considered a hybrid scheme? Like, when do you decide for which sockets to intercept and offload and for which not?
Yeah. Our current implementation is trying to capture all the system call and trying to offload everything to the NIC side. But maybe kind of filtering option can be easily implemented in the future. So I think it's selectable.
Can we deal with this side of the V, please? Next. This side.
I have a question that's,
If you don't mind. You've been waiting for some time.
Okay.
I have a question that's maybe more for the audience than for the speaker. On the one hand, I totally get the reluctance to do complete offload of TCP to the NIC. I understand there's a tremendous number of problems associated with that. But at the same time, there is a reality here, which is that networks are getting faster at a prodigious rate with no let up in sight, and CPUs are not getting faster. And so fundamentally, I just can't see how it can make sense to implement transport protocols in software going forward. You know, if you look at TCP, my measurements suggest if you're running mixed workloads, you need about 1 core for every 10 gigabits of network bandwidth, more or less, with a factor of 2. So that means 10 cores for 100 gigabit network, 20 cores for 200 gigabit network, 40 cores for 400 gigabit. And furthermore, even if you can afford to put that many cores on it, coordinating that many and actually trying to spread the load evenly is pretty much impossible. And so then you end up with hotspots and you actually can't use, I defy you to build a system where you can really use 40 cores with load spread evenly across them. You'll end up with most of the load on 1 or 2 cores and you won't be able to use the full network bandwidth. So anyhow, it seems like sooner or later, we have to figure out a way to get over this hump. I'm curious, you know, can anybody see any way we could ever get to the point of doing a full offload, and what steps would we have to go through in order to get there?
Okay, so the question you're raising, we know that hardware is going to be needed at some level. The problem we've had for so long, and we talked about this previously, it's really, really difficult to do offloads of complex things. TCP offload, and I'll mention this in my talk, TCP offload engines were an unmitigated, complete failure. From the point of view, they didn't work. Now, the reason they didn't work was because exactly what you said. The second you put something that complex into hardware, we've lost all the value, all the benefit. We've lost the ability to add new congestion algorithms, to do this, to do that. And the performance benefits then become questionable. So it's a double-edged sword.
Can we defer this discussion to the breakout, please? I'll let that gentleman ask a question because he's been waiting, and that's it. Who's the next speaker? I'm sorry, is it you, Tom? Ari.
Yeah.
But so there's a question that's on the board. Maybe you want to answer that quickly, and then 30 seconds for that, 30 seconds for you. I'm sorry, I know. Yeah.
The packet reception work as is, as kernel has how Linux kernel implemented. So the Linux kernel library is a part of the reception and trying to forward to the user space application by a system call. So that's almost similar to how the typical kernel implementation does.
Yeah, please go.
Yeah, I'm kind of following up on what people said earlier. I think the thing I would have liked to see from the benchmark is something like bits per joule. So you're evaluating what the offload is actually doing, because I mean, the way I've thought about it is you could put together a system where the SmartNIC CPU is basically the same CPU as the host processor. So what are you actually doing? You're just stuffing more CPUs in the box, right? It needs to use less power to serve the same amount of data, right?
Okay, so there's a BOF tomorrow. Sorry, not a BOF, but Jesse, breakout tomorrow, power, networking. Come to that, please. And you too, Hajime. We'll give him a round of applause, please.